Department of the Geographer's tent. What in the world are you taking pictures of?
It's my travel candle.
Oh, it goes everywhere with you.
Yeah.
So you've entered the Department of the Geographers. We are surveyors and map makers to General Washington's Army. We would be dispatched roughly 2 to 3 weeks ahead of the Army, and they needed to know where roads would take them, where they could bed down troops and livestock, and that was our job, is to map that out and rush these rough drawings back to headquarters for troop movement.
66?
Yeah.
90% of the equipment you see in the room is original. Was made in the 1700s. This pantograph was roughly 1750-ish. Our drafting instruments are all original. And the compasses, circumferers, and that thing that you see outside.
So it also plays
I know
into
the
an acre.
circumferer was
An acre being
built by
10
William
chains
Collier
by
in
1
1720.
Okay.
You go out in
I
like a
can never
museum, you
remember
can
how many
touch
feet
it.
are in a mile, but I can
Take a nice
multiply
look at it.
6 times 8. So
Being treated
also
to quite
a rod,
display of
all
history.
of these are division.
The maps you see on the table over here
So what Mr. Gunter did
are
was
copies of maps from the Library of Congress that our unit produced during the Revolutionary War. These are actual maps that were handed back to the
is
Army.
he
for
takes
troop
this and
movement.
by making it
We know that there were over
100
400
blanks,
drawings
he actually lets them
done by this unit. 283 of them still exist,
42 blanks,
and they're for public
7.42.
viewing in the Library of
And
Congress.
when he
Yeah.
wants to take
Inkling
those
go take a
distances
peek
and
at
apply
it.
them to paper,
But
he comes up with the Gunter scale.
this is a good example
The
of
slanted
what
lines
our
in
unit
this
did produce
grid
during the Rev War.
will actually,
You
as
can
they
see it's
go
on a need-to-know
down,
basis.
each
It
line
depicts houses,
will move
depict where the roads go.
1/100th of an inch.
Some hills are noted
So,
by the hash marks.
because
So
of
it
that,
shows a
you
little
have
bit of the
42
terrain,
links.
but
I can
nothing
go
really in
over
detail.
4, down 2.
Elevation
and
was
where that
something that was
intersects
not charted
from
at the
Each
time.
line is going to be 0.42 of an inch. So he can
But
take
we
his
could
dividers, I think,
we
are
could
back
determine our
over. He can
position
spread
on
his
the
dividers
face of the
out
Earth
to
through
however
latitude and
long.
longitude.
Chains,
And that's the difference between a geographer and a surveyor. A surveyor will tell you, well,
a local
starting from the big oak tree on Joe's property, I went out 200 chains on a 300-degree bearing.
So this is, basically. the
Unlike
tools of
that,
a
the
local
geographers
surveyor.
could tell you through
This is
lat
where
and
you start
long,
getting into being a
latitude and
geographer.
longitude, exactly where he was on the face of the Earth. It was quite a discipline back in the 1700s. There was only a few people in the colonies that were able to do that.
When you were doing the surveying, do they take?
So in order to do that, we use the octant, which is on the
how much
table
precision
behind
do
you,
you
the
have?
triangular
Do they
Well,
count half
device.
of-
No, they don't do halves,
we could
but
shoot the sun, celestial bodies.
7.92
And
inches.
that
You're going to be plus or
would
minus
give
4
you your
inches,
longitude. In order to
because of the
determine
way
your
things work,
latitude, you needed
over a long distances, they're going to average out.
Yeah, you
They're
had a
gonna
good,
average out
good
too. You're gonna
chronometer,
have
good
generally
timekeeping
many
piece. You can
over as
determine
you have under.
those two
In
items
the odd
and
circumstances.
pick out your spot on the face of the Earth.
So, yeah, and you're looking for an accuracy to
So
record your scale.
there's Gunter's chains on the table.
Right here,
Gunter's chain. It's 66 feet long.
Or this one.
It's 33 foot long. Dang teachers. So, well, they typically used to have a chain, just to pull a full chain, pull 66 foot of that through weeds and bushes and stuff. It was very tough to do, so they pull a half a chain. But why in the world would we measure in 66 foot increments? It's kind of a strange way to measure, isn't it? But it had precedence. It's an English measurement. And if you took one chain by 10 chains, that's 1 acre of land. 10 chains long is a furlong. 80 chains is a mile. A quarter chain is a rod or a pull. So that's why they use that measurement. But the significance of the Gunter's chain is Edward Gunter took that chain and he divided it into 100 equal lengths. Okay, 7.92 inches per length. Now you've got a divisible number. 100, all you got to do is move decimal points. It becomes somewhat metric, doesn't it? And to complement that, we have the Gunter scale. The Gunter scale is used like this. Each one of these is one chain length. So 1, 2, 3, 4, 5 chains long. These represent the lengths of chain. So if I have something that is one chain, 64 lengths, I come in on the 6, I drop down to the 4, there's 64 lengths of chain. I move out here, there's one chain, 64 lengths. I can now put that distance on the paper, and it's to scale. All right. Well, we got the distance portion figured out. Now we need a direction. So my surveyor would come in, and he would tell me my first reference is a 300-degree bearing. So I've got a true north and south line on my paper already marked, and I had my 0 reference line. So I align my protractor with 0 reference. I come over here to 300 degrees and I make a mark. Now I know the bearing. and I take my parallels and I align it with that bearing. Problem is that's not where I want to draw my road. I want my road over here. So I now take my parallels and I walk them over to where I want to make my line. Now I can do my bearing, right? And that's how it's done. And then I plot my distance, take care of that line, and then I start plotting my next bearing and distance. In that fashion, you actually end up with a map. And if I can find it in here, you can actually see where they set stations up because of the dots they put. And you can see there was just bearings and distances taken the whole way. And this is a pretty good example. Each dot represents a chain pole and a distance and a bearing. And you can kind of see where they made these dots down the paper to show their stations. That's how it's done. Unlike the maps that were done on the wall, as I explained earlier, they're copper plate engraved maps. They were done, it would take years to produce those. And it was all done by engraving copper plate. But the reason being that they can now put it on a primitive press and make several copies of it. Ours, if we wanted a copy, we're down to the pantograph and reproducing them that way. So the pantograph is actually making a half copy of what you see right here. And a better example of one that's already completed is we did a half copy of the Morristown map. So there it is, and that's what this piece is. Yeah, we're really cool, huh?
That's pretty impressive.
It is impressive, yes. They had the same mind as you and I, and they just had more time without TV. So they kind of use their brains a little bit more than we do.
Said that.
Absolutely.
I always talk about, we always forget that while you lack certain technology, you still are humans and you're still intelligent. And even though this is not on subject, a lot of people underestimate the intelligence of the Native Americans. And this is a Stone Age technology that negotiates and plays the British against the French and the French against the British masterfully. And you're like, no, they're people, they're humans. We have the same brains. We just, see pictures of this device. Actually, come on in a little bit more.
Before he even gets into that, you talk about technology, and I'm going to let him go. But you should show him the small astrolabe there and tell him that guy right there is Arabic in invention, and it was developed in the 16th century. And they used it for navigation, not on sea. They had to navigate the desert. And there's no landmarks in the desert, and it's always changing. So think about that. In the 1500s, the Arabics come up with that technology.
You could actually tilt it and get an angle to it.
So he is going, so he's going to show you what follows that.
You've seen one of these before in a picture of somebody on a ship, probably. And you don't really know how it works because it looks strange and it looks like, whatever. If there's 6 of them in a circle, sextant, 8 of them in a circle, it's an octant, 1/8 of a circle. And it's got a rocker arm here. This is a mirror, and as I move this arm, that mirror's going to rock, okay? It's also got a mirror here, and a piece of glass there that I can see through simultaneously by looking through the holes, right? So what I'm going to be doing is I'm going to look at a celestial object.
It is.
And I'm going to bring it down to the horizon, okay? I can look through here. If I'm at sea, I can see the horizon through the glass, and I bring like maybe the reflection of the sun or reflection of a star down. And if it's the sun, I'm going to probably put these shades out here so I don't stare at the sun. But basically, I'm going to bring that down so that the sun lands right on the horizon. And then I can measure the angle to the sun. Okay. I can also use this to measure between different celestial objects. You might be able to get the angle between Mars and Arcturus at a particular time of day. This is also going to let us know, what does noon mean? And don't say lunch. Highest point of the sun in the sky. We have no time zones yet. We don't have time zones until the trains are running and we want to be able to have nearby cities have the same time. So we're going to be able to measure, and if I'm good at this, every day I'm going to measure to the highest point, but I have a horizon line to use, and I'm measuring off that horizon line. And when it reaches its highest point, I'm going to go to my timepiece, and I'm going to look and say, oh, my timepiece is off by 28 seconds, just like it was yesterday. And I'm going to readjust it, but I'm going to know how fast or slow my timepiece is. Because if I take a measurement later on, I can then extrapolate the offset that I should have seen on my timepiece. Well, what does that give us? Well, to figure out where you are on the planet, you're going to need to know how far up the planet you are from the equator. You can use the angle to the North Star. Somebody here is going to see the North Star at a different angle than somebody here. And you can use the sun. the angle to the sun at noon, depending on what day of the year it is going to be at different height. And you can cross-reference that and figure out how high you are up the planet based on that number. And now you have an accurate timepiece. You need that accurate timepiece to figure out how far around the planet you are from some other place. So what are the points of reference? You have Madrid, Paris, and London at Greenwich, England. They all have observatories, and they are making celestial predictions, and they're publishing those starting in 1766 in these almanacs. Now, we have two originals here. This is a 1778 original, we have a 1779 original here. And when you go to the back of these, you can actually see the charts, and they will be predicting, telling you when the moons of Jupiter are eclipsed, when they come out from behind Jupiter. So we're using satellites. We're using satellites of Jupiter, and so, or we're using angles to stars, right? And so let's imagine if we're standing in a field, and you have a building out there, and somebody walks around the building. And because you're on that side, the angle between you and I is going to determine who sees it first. But if you look at a celestial event, it's so far away, no matter where you are on the planet, the angle between us is irrelevant. We are going to see it at the same moment in time. But we have different noons, okay? So if Greenwich, England tells us that an event occurs at this time, and I see it at that time, I can figure how far around the planet I must be. We're comparing our noons, okay? So 24 hours in a day, 360 degrees in a year, that sun is sweeping around the planet at 15 degrees an hour. So, yeah, here's the thing. Sometimes people will come back and they're like, I didn't get it. And here the second time, like, oh, it was so easy, I feel embarrassed. They're like, no, you were overthinking. It actually is, it's not just there. So that's what it's going to give us, those measurements. Over the period of time, after these almanacs start getting published, the French are still using the French point of reference. The Spanish are still using the Spanish point of reference. So if you get a latitude and longitude on a French map, it can be different than the same point on an English map. But eventually, everybody agrees that predictions from the Greenwich, England almanac are the best, and we end up with Greenwich Mean Time because everyone's going to agree that's the standard we're going to go to. So I talked about doing that on land, on a ship, right? Well, if I need an angle to a celestial object, but I'm not at sea, how do I get an angle to a celestial object? Huh? You're taking that outside?
I'll bring it back.
It's his, by the way. Almost everything here is. So if I'm at sea, I can get a horizon line. How do I get a horizon line to measure off of when I'm standing in a field or I'm in trees, right? Well, I can use an artificial horizon. If you play, anybody play pool? You shoot a ball and it bounces off the side, it comes off at the same angle. The angle of incident, angle of reflection. So, make an artificial horizon. Got a tin container here. Guess what that is? What's this?
Plastic.
Is it a prism?
We don't have plastic yet. This is actually mica. It's really thin shaped rock. So thin you can see through.
Wow.
Put that over top so that the wind doesn't disturb the surface of the liquid we're holding here. We use mercury. Nice thing about mercury, highly reflective surface. It's going to self-level. The liquid's going to self-level, right? And when you pour it back in, it's going to self-gather right back in. So mercury's a good move for that. So it doesn't matter how I set this, that liquid inside is going to be perfectly flat. So rather than take an angle from the horizon up, I can actually look at the reflection in the same device and instead measure the angle down to the reflection by using like a palm and keep the device level. And basically getting an angle down is equal to the angle up. Not too hard, right? Do that anywhere. I'm going to take into account the time, how much time. I'm also going to take into account how far up the planet I am, because I'm looking through more and more atmosphere as something gets lower on the horizon. So those calculations get a little bit more intense than the land surveying locally. Land survey locally, you can teach anybody that has had high school math and did well on it, you're going to be able to do a land survey. But the geographers are going out and telling you where we are on the planet. Okay? We also have some other really cool things here. This is magnetite. This is naturally occurring magnet. It's got high iron content in it. And if you cut this and shape it, you can actually increase the effect by giving it, actually it's got a north and a south pole on a magnet. And we can then use this to remagnetize our needles. Actually, wealthy people. My keys just came out of my pocket.
No, I need them.
Wealthy people are going to have these. What that really means is she's making me more clothes, so I'm happy about it.
Everybody's happy about that.
Yeah. Hey, listen, I've got a picture. There's a sketch of a guy wearing this combination.
Tell all your secrets.
Before the war, ditto suits are very popular. Ditto meaning same as, and that's the term during the period. You have a lot of, he went and ordered a coat and a breast, everything the same. And after the war, you start getting this fashion where he ordered a checked waistcoat and a striped pair of pants and a polka dot coat. I had a little kid on Friday tell me I looked like a puppet. Hey, I thought I won. I thought it was great. And the embarrassing thing about it is when I started this hobby, I actually found these guys. These guys have been doing this for a lot longer than me. I've known them for a few years. And most of the stuff is Tony's. And I found these guys and I'm like, oh, I gotta get a regimental. It actually look official and stuff like that. And my wife goes, where are these crazy clothes? But you realize when we were trying to convince you to join the hobby, you were like, I don't feel embarrassed wearing the clothes.
It grew on you.
There's lots of equipment. I can only explain a few pieces. These are the jump up. There's a lot of other jump up. The piece on the table there that lets you resize, that's awesome. I used to have a plastic one as a kid.